Okay, before we move on to next topic, I would like to add some discussion on stability analysis that we've done before. So stability, linear stability of finite difference approximation of differential equations. When we derived when we used von Neumann method to obtain some stability criterion or restriction on time step, we basically found parameter mu, or this current number, for which stability is assured, or this amplification factor is actually smaller or equal than 1 for all harmonics of waves that could be represented on a grid. And of course, well, that's basically absolute linear stability. But at the same time, you need to realize that amplification factor can be very different for waves of different wavelengths. I would like to give you one example. So let's consider our favorite scheme, which is upstream bias scheme, first order in time and space. Just as an example, of course it's not a very good scheme, but as an example, so let's consider it, and I wrote it several times, so let me repeat here. Where so it looks like that, where mu is our current number, it's like C delta T divided by delta X. And we remember that stability criterion for the scheme is mu should be smaller or equal than 1. So when we derived stability amplification, the expression for the amplification factor, lambda, so we assume that our solutions are represented as some lambda in the power of n times e to the sum I alpha, which is like, and then we alpha k. So we then substituted it to our equation, and then we would find our expression for amplification factor lambda. So for this equation for upstream bias, our expression looked like the following: is lambda was equal to 1 minus mu 1 minus e to the power of I alpha. And then from that, remember we used this complex plane to graphically show that for lambda, absolute value of lambda, to be smaller than 1, you need this condition to be true. So that's fine, but the thing is, like, of course, that would be true for all alphas, and but how is this? Lambda is not the same, obviously, for particular given alpha. First of all, what's alpha? So this alpha here, as I mentioned last lecture, it of course depends on particular wave length, and alpha is generally in the range from, say, 0 to pi, and 0 being the longest possible waves, like actually infinitely long waves, and so alpha is 2 pi times delta x divided by lambda, so it's k wave number times delta x. That's what alpha is. And of course the shortest waves that can be represented on the grid, I mentioned that, so minimum lambda, here wavelength, not this lambda. Maybe let's use L for wavelength, just not to mix it up. So minimum L minimum equals to 2 delta x, so that alpha maximum equals to pi. And of course, for infinitely long waves, alpha approaching 0. So alpha generally is some range from 0, which is open. It's not cannot be exactly be 0 to pi interval. So what if we so what's amplification factor for different wavelengths? So let's so if we write this alpha as 2 pi delta x, and then L is some n times delta x, so it's number of delta x in a certain wavelength, how many delta x's you fit in this wavelength. So we get that alpha is 2 pi divided by n, so that n equals to 2 pi divided by alpha. So amplification factor is a function of this n, or function of this alpha. So absolute value of lambda equals to 1 minus mu 1 minus cosine alpha squared plus mu squared sine alpha squared, and the whole thing is square root. So this is the amplitude. So you see that amplitude is a function of alpha, and alpha depends on wavelengths, or how many delta x grid spacing, how many grid spacings you need to represent that particular wavelength. So I did some simple computations. So what's the point here? My point here that, of course, for mu greater than, in this particular equation, for this particular scheme, any mu greater than 1 will create instability, but if you look at it, when mu equals to, say, 0, of course it's always stable. Well, mu equals to 1, they're all stable. When you start increasing mu, of course, your amplification factor becomes bigger and bigger. And I remind you what amplification factor is. It's basically factor by how much amplitude of waves increases in one time step. So from one time step to next one. So if amplification factor is 2, then on a next time step, the amplitude of waves will double. And of course, that's not good thing, because if it keeps doing like that, eventually it will be kind of very unphysical solution. But what if your amplification factor, say, 1.01? So it's only 100. So next time step it will increase only 1%. Would be a problem? Actually, it may not be a problem, because in addition to advection, you may have, say, some diffusion in your model, or some physical diffusion that you, or some subgrid scale kind of diffusion. So explicit diffusion, not this implicit numerical diffusion, but associated with the scheme, for example, but explicit diffusion. And that would actually try to reduce the amplitude. And if you found some particular kind of large enough, not too large diffusion coefficient, then it would probably fight this amplification factor of 1% very efficiently. So this is a table. So here is n, so number of harmonics, a number of grid spacings in one wavelength of harmonic, and this and here I have different mu's. So here's mu equal to 2, which is pretty considerably above our mu equal to 1. And here is mu equal to 10. So our time step is 10 times longer than required by the stability. So definitely model will blow up, right? But which waves actually will blow up? Of course, first going to be shortest waves, but what's the difference between longest and shortest waves? So let's say that for wave number 2, so 2 delta x waves, here amplification factor is 3. And so this is lambda 3, and here is 19. So you see that in this case, when your time step is twice as long as maximum allowed by stability criterion for the scheme, next time step, your amplitudes of 2 delta x waves will be 3 times bigger. While for mu equal 10, it's 19 times bigger. So in one time step. So one time step, it's 19 times bigger already. So this is very unstable, right? For wave number 4 delta x waves, it's a little bit smaller. It's 2.23, and here 13.4. So you see it starts reducing. And how about wave number 60? So 60 delta x. So if your delta x say 1 kilometer, those waves are 60 kilometer long. Yeah. So it's you can actually resolve storm with this many grid points quite well. So for that you have amplification factor of 1% for mu equal 2, and much worse for mu equal 10. It's 1.4. Now, how about waves 180 delta x? Then this one becomes 0.01. You see how small it is for mu equal 2? And for mu equal 10, it's 5%. Well, it's becoming much better. And for 360, say, so for our 1 kilometer grid, this is long waves, like 360 kilometer phenomenon. It can be some frontal boundary, maybe cyclone. Actually, it's smaller than cyclone. So it's pretty big phenomenon. Then, it's very big storm. 360, and here we have 1.0004, and here we have 1%. For mu equal 10. So for mu equal 10, these waves effectively are stable because just little diffusion, explicit diffusion, will handle this. Well, you may ask, so what's the point of all this? Of course, in your solution, all these waves are present, and these waves will ruin solution regardless of how stable, how barely stable these long waves are, because they will get unstable first and will ruin the solution. Of course, you may say, well, maybe you can filter them. So you can use your Fourier filter. You do Fourier decomposition of your field, and you remove all the Fourier harmonics that are shorter, say, than 180, make them 0, and you do Fourier synthesis. You kind of make reverse your Fourier analysis back to Fourier synthesis, and you produce field where all these short waves are filtered out, and then your solution will be stable for very long time steps. So why not do that? Why we bother with those? But because if you do that on a normal grid, like rectangular grid, why you even have this high resolution on that grid if you filter all these waves? Because effectively, this is the resolution you will be running. This is your smallest resolution if you filter all the waves, say, shorter than 180. Then your effective resolution is not 1 kilometer, it's 180 kilometer grid. So you're wasting all this computer time, and storage, finding some solutions that you're going to filter out only leaving long waves that are stable or relatively stable. So for normal simulations, of course, nobody would do something like that because that defeats the whole purpose of making a high resolution grid. However, there is one application of this technique, or one application of this fact, that longer waves are much more stable or much less unstable or marginally unstable than shorter waves, is so-called polar filtering. So basically, if you have latitude-longitude grid and you have globe, so you have the globe, and then you have latitude-longitude grid, which is very common in climate models, for example. Well, maybe not now, for different reasons. It's mostly for very lack of good or not very good performance on parallel computers. So people now switching to so-called geodesic grids, and we're going to talk about those grids in some due time. But right now, like, there is this latitude-longitude grid, and here, as you move to the pole, your resolution very quickly becomes very high in the zonal direction around the pole. So in this direction, it's kind of can be stayed the same, but in this direction, along the latitude circle, it's actually or around this circle, it becomes high and high and high, and eventually, and of course, this is local stability criterion. So your time step required to do your computations becomes smaller and smaller and smaller, and you cannot run small time step here and long time step here. So everywhere it should be the same time step. So effectively, your pole resolution around the poles will dictate time steps that you should use in your simulation. And here, this thing becomes very handy. So what you do, you actually filter your solution along this direction. You apply Fourier filter, or you do this Fourier analysis first. You compute Fourier harmonics, amplitudes, and you zero, depending on how close you to the pole. So the closer to the pole you get, the more harmonics you filter, so that the remaining harmonics will be marginally stable. So you could use just diffusion, explicit diffusion to actually, because these amplification factors can be very easily managed. They're not gonna blow up your model very quickly. So this is what is done, has been done in climate and GC climate models and general circulation atmosphere, general circulation models that use latitude-longitude grids, regardless of numerical methods that they use. They basically apply this polar filter to make stability constraint, to remove all these very unstable short waves and only longer waves. But like, if you're really interested in big waves like that, let's say some wave here. So here, it's equivalent size. It's basically very long waves. Here they may not be very long waves, because here you have resolutions coarser than here. So effectively, you don't really disturb much long, large-scale circulation, large-scale waves. What you're filtering is the small-scale kind of features at the equator. It's not gonna, they become very too small features at the pole, and so you basically just remove and make a resolution around the globe kind of uniform, effectively. Even though your grid making resolution, actual resolution very high at the poles, but by doing this near the poles, but by doing this filtering, you're basically making resolution effectively the same everywhere, at the equator and at the pole, the same kind of resolution. And this is how you do it. So you remove all the short waves, and you leave only these longer waves that are marginally stable. And again, the amplification factor of instability is very small, and you can manage it. And that's that's how it's done on those type of grids. It's called, so it's polar filter. So there are many ways you can do it intelligently. So there are many articles written on this subject, how actually you choose which harmonics to filter. But generally that's basically the case. The closer you get to the pole, the more harmonics you filter out, and so on. So that's all I wanted to say about this topic. I think you need to realize that stability is all about short waves. So short waves always get unstable first, and longer waves get unstable later. So sometimes you, by filtering your solution, you may actually increase stability of your scheme. But of course, in a normal case of a uniform grid, that defeats the whole purpose of having high resolution. But on this kind of grids, when you have non-uniform resolution, actually this kind of technique, filtering, can be very beneficial. And sometimes the only way to do anything useful, because if you don't do this on a globe with latitude longitude grid, your time step would be so small that you wouldn't be able to do anything. Okay, so next we're going to talk about how to improve forward in time schemes to make them stable and offer some higher order of approximating. What I mean by that, before we considered this earlier scheme, which is a forward in time scheme. It involves, so we have phi n plus 1 minus phi n divided by delta t. And this is forward in time scheme, just two levels here, n plus 1, the future, the present, and equals to some right hand side. Like in the case of advection operator, we have like minus c. And then when we use upstream bias scheme, we have this stable scheme for certain mu, like mu should be, or this current number should be smaller than 1. But unfortunately, that scheme is only first order accurate. It has truncation error in time and space of first order. So this is not very good scheme, and it has very strong implicit diffusion or numerical diffusion that smooths the solution too much. So nobody really wants to use that in real applications, in most applications, especially in our field. So we would like, of course, to use some higher order approximation in space with this scheme. Like if we try center differences, which is second order in space, accurate to the second order in space, we couldn't do that because this scheme is absolutely unstable. And so if you use try other schemes, they will also be unstable. So this scheme is only this forward in time scheme if you use on the right hand side only present, like present solution, and any other approximation basically in space, any high order approximation beyond upstream bias, which is first order, will be unstable. So it seems like we cannot use this very convenient and nice earlier forward in time kind of matching scheme. It's very convenient. You just have present, you forecast future, you make it present again, you kind of jump forward by one step. So instead we tried to make it stable by using leapfrog scheme. So but now we need to move to one more time step in the past, and then we have the same right hand side. And this one is stable for mu smaller than or equal than 1, which is okay. and it's leapfrog scheme. And last lecture we discussed it, and this is okay scheme. It has simplification factor of 1 for all harmonics, but the problem is that it has this computational mode, very strong computational mode, which is not damped, so it's always present, and it has the same amplitude as your actual solution, and it propagates in opposite direction to actual solution, and moreover, it's actually flipping sign all the time, from plus to minus, from one time step to another. So that's very disturbing behavior. Of course, it can be dealt with using Robert filter that we discussed, Ruben Ellison filter that we discussed last time, but it's kind of little bit, I don't know, it's kind of not very, I personally don't have very high degree of confidence in such an approach. And here you also have to keep like additional storage for n-1 time step, which is not, of course, a problem. Right now, in current computers, usually storage we have now very large memory, but still it's kind of the existence of this computational mode is a little bit bothersome. Also, the disadvantage of this approach that diffusion actually is unstable on time step n, so you need to use diffusion operator, actual diffusion, on a previous time step n-1, then it becomes stable. So your future solution on time step n+1 depends on some solution which you diffuse on two steps in the past, not one step in the past, but 2 steps in the past. It's kind of weird a little bit. So, is there some other way? Can we actually still use this forward in time scheme like here, and still use centered like high order approximation of derivatives in space? Actually, there is such a way, and that's what and there are actually many ways of doing that, and that's what we're going to discuss next. So let's for that, basically what we need to do in our right hand side that we used before on this earlier forward in time scheme combined with central differences in space, it's unstable. It's because we actually used right hand side on a time step n. What we use right hand side on some other time steps, or some mean, or some kind of weighted mean of previous time steps like n-1, or maybe use implicit scheme and so on. So generally this is what we approach this problem like as a, let's consider it's only time problem. So we have a general equation like d phi dt equals to some right hand side f, which is a function of x and t. So we want to approximate this time derivative as forward in time scheme, like phi n+1 minus phi n divided by delta t. But right hand side will be not necessarily time step n as we used before, but some combination of various this function on various time steps. So it could be like some coefficient n+1, and f is evaluated at time step n+1, plus b, or actually a n times right hand side at time step n, plus a n-1, f n-1, plus, and so on. So in those coefficients a n minus 1, and so on, this is what we will find to find various degrees of approximation in time for this original equation. So so when generally when you have right hand side that depends on the future time step n plus 1, that scheme called implicit scheme. So this is implicit, and the problem with implicit scheme is, of course, that you then need to solve a system of linear algebraic equations. So you need to invert very large, potentially very large matrix. If it's nice matrix like diagonal matrix that we considered back in some previous lecture, in case of diffusion, for example, operator in one dimensions, or even with advection in one dimension using second order central differences, for example, and using n plus 1 time step, then that scheme would be unconditionally stable. It would be stable for any time step. So this is very nice property, and using tridiagonal solver, it can be fairly quickly to actually find the solution. But it's only true basically in one dimension. That's really easy. But what if you have three-dimensional problems? Then in 3 dimensions, it won't be some easy, nice tridiagonal matrix anymore. So then you would it would become very difficult problem. There are ways to approach that. It's basically by splitting in directions and finding kind of one solution in X direction, one solution then in Y direction, and then solution in Z direction, kind of so-called directional splitting. But we're not going to talk about that today. But generally this is kind of difficult to solve in 3 dimensions. So if you have n plus 1 time step on the right hand side of this equation, that scheme becomes implicit. But if you have only current time step and previous time steps, that scheme is explicit. And explicit schemes always have some stability constraint on time step. So unlike implicit schemes that don't have a generally stability constraint on time step, explicit schemes, they always do have some stability constraint. And moreover, the more terms you use here, the more restrictive the scheme generally becomes. So in general, time step becomes smaller and smaller. Unlike, say, when you use only time step n with, say, upstream bias scheme. So let's find some general how you approach it, how you find these coefficients. For that, of course, we use our favorite method, which is Taylor series. So let's write left-hand side, applying Taylor series. So Taylor series, Taylor's expansion around time step n. So we have this guy. So I will write it right away as d phi dt, then it's times dt, and divided by dt is going to be like that, plus second derivative times delta t squared over 2 divided by delta t, so it becomes delta t over 2, d phi here, plus third derivative phi dt cube dt squared over 2 plus and so on, plus some or of delta t cube. So equals to right hand side. So now we expand right hand side the same way, but now we have this summation of terms. So we have sum from L equals to some minus k to L equal to 1, which is our implicit scheme of coefficients a n plus L times f at time step n plus L. This is just index, it's not power, in the power of n plus L. So, now let's write it explicitly. So we have sum of this L, I won't repeat it, A n plus L, and here you have F. So you linearize it around n. So you have f n plus df dt, Taylor series. Now delta t here depends on L. If it's L equal to 1, then it's delta t equals to n plus 1, so minus n, it's 1 delta t, and so on. So it should be L delta t and plus second derivative df dt L delta t squared divided by 2 plus second derivative f delta t squared. Oh, actually here it's already squared. Sorry. So it's cube now. Cube L delta t cube divided by 3 factorial, which is 6, plus so on, plus or of delta t4. So now, so this is general expression, and now we notice that we can use this equation to replace these derivatives here. So d5 dt becomes f. Second derivative of dt becomes df dt. And third derivative becomes d squared f dt. So now we have kind of nice correspondence between those two. All right. So this is our kind of approach. So let's keep it for now. So now let's apply it for various types of schemes. Let me write it here. d5 dt equals to f. So this is various schemes that used to solve this type of equation, which basically all our equations can be written like that. The right hand side can be advection, diffusion, other processes, and left hand side is some tendency of velocities, of momentum, of temperature, of water vapor, whatever. So this is kind of general equation of a prognostic equation. So let's do some classification of the scheme. So first is Euler scheme, right? We already mentioned that. Euler, which is phi n plus 1 minus phi n divided by delta t equals to right hand side to the at current time step. This is Euler scheme, and we use that for our upstream bias scheme. And unfortunately, if f represents centered in time advection scheme for advection, it's unstable. But f may not be necessarily be advection, it can be some other process like diffusion. For diffusion, it would be completely fine. It would be stable with some criterion. So this Euler scheme, accuracy of it is delta t, so it's first order in time, which is not particularly good. So second scheme, which is more useful. Let's try the following scheme, and it's called Adams-Bashforth second order. So second order Adams-Bashforth scheme. So this is general Adams-Bashforth schemes. So this general family of schemes that basically have very similar structure, just different right-hand sides. So this scheme would be like phi n plus 1 minus phi n divided by delta t. So it's still forward in time, but right-hand side would be some coefficient a n or L in this case. A n f n plus a n minus 1 f n minus 1. So basically what we do this kind of linear interpolation between time steps n and n minus 1. So what were those coefficients? The first instinct would tell you, you would be inclined to say, okay, it should be 1/2. So 1/2 of this plus 1/2 of this, but that scheme would be unstable. That's incorrect actual approximation for this equation if you want to approximate it using this. So let's use this to approximate it. So for this case, what's else? Values of L are 0 and minus 1. So n minus 0 and n minus 1. So L equals, like we used here, equals to minus 1. So let's now make it work. So we have two coefficients. So first condition, if you look at this, that in order to make these terms disappear on the right hand side with fn, you need sum of all the coefficients to be unity. That's first condition for anything. So you have that a n plus a n minus 1 should be 1. That's fundamental condition in this case. So now let's use next term, which is df dt. So what we have here, we have a n, and for a n, L equal to 0. And this means that there is no such term for it. So there is no a n for this case. Then you have a n minus 1 means that L equals to minus 1. So now you have what? L minus 1, so it's, and forget about delta t, because delta t here. So it becomes minus a n minus 1 equals to, so here's minus 1 equals to, and here 1/2. And from that you have that a n should be equals to 3 over 2. A n minus 1 equals to minus 1 over 2. So this is, so it's not 1/2 plus 1/2. It's actually 3/2 of this minus 1/2 of that. So this is, and this is called Adams-Bashforth second order. So let's write it here. 3/2 minus 1/2. So it's kind of nice, simple scheme, and it's approximation of second order, so it's O delta t squared. So it's second order, even though it's forward in time, but it's because we use this this weighted mean of the right hand side, we actually raised the order of this approximation to second order accuracy. So you see, you can raise it not only by using second order derivative here. Here it's still first order kind of looking derivative, but by using this, you actually cancel those terms like here, this expansion term for this derivative, by using right hand side in this form, and then you cancel this this derivative here, so it becomes second order, which is left, second order truncation error. Okay. So this kind of looks nice and simple scheme. Can we use it? Well, kind of yes. It's pretty popular actually scheme, especially in engineering flows like DNS, direct numerical simulation, large eddy simulation, and unfortunately, this scheme is combined with central differences, say central differences, high order kind of differences in space for advection. It's also unstable, like earlier scheme. Fortunately, this amplification factor for short waves for this scheme is relatively small. Unlike this scheme, when amplification factor that we considered could be very large for short waves, for shortest waves that can be represented on a grid, for this scheme, it's unstable, but it's not that bad. It's not that big amplification factor. So by using some explicit diffusion, which you always use when you use large eddy simulation technique, for example, or if you use direct numerical simulation technique when you have actual diffusion coefficient of viscosity, say, of your fluid, that allows it to manage this instability, this very weak instability, and that's why people use a scheme, because it only requires, it saves you a lot of storage. It requires only 2 arrays for right hand side. So that's a nice thing. But it's kind of weakly, very weakly unstable, as I said before. So what else? What else I wanted to add to that? Well, kind of forgot. Okay, so that's nice, but that's a drawback, that it's only weakly, generally weakly, barely stable scheme. That's why people kind of a little bit worry about that scheme. Although I use it very I tried it. I never seen instability with this scheme, with large eddy simulation. It's always works just fine. So that's okay. But if you, another computational mode. Does this scheme have computational mode? Yes, it does, because it uses 2 time steps here. You see. So and so your amplification factor actually has 2 solutions. Again, it's when you substitute this for a particular form of advective operator, you will have 2 amplification factors. One is going to be physical solution, and second one is going to be computational mode. But unlike leapfrog scheme, when this computational mode was the same amplitude, it was not damped, so it was kind of, unless it's artificially damped, it would just linger around, and it moves to the left and stuff like that, some nasty behavior. In this case, there is computational mode, but it actually can be shown that it's damped. So there is some implicit diffusion, which is relatively strong for this computational mode. So over time, it tends to decay. So usually that's why people like this kind of schemes, unlike leapfrog scheme, because it's still second order in time, like leapfrog scheme, but it damps computational mode by scheme itself. So you don't need this artificial filter to artificially suppress this computational mode and so on. It's already built into the scheme itself. Okay, so now next one, let's consider next one, and it's Adams-Bashforth third order. Well, third order, and this is very popular scheme. In fact, in my model, in SAM, this is the scheme that is used for advection of momentum. It's been around for very long time. I kind of like this scheme, and it was a it was my choice because of this nice property that it's actually stable for advection for advection of second order in the right hand side. Of course, the criterion is not like 1, current number 1, it's slightly smaller, but still it's stable, so there is no this kind of possibility of even possibility of some linear instability if you follow your current your restriction based on current number, unlike second order Adams-Bashforth scheme, which is only kind of weakly unstable, always weakly unstable. So let's exercise again using this kind of approach to derive coefficients. So now we have -2. So now we have this scheme, which is phi n plus 1 minus phi n over delta t, still forward in time, but equals to this a n f n plus a n minus 1 f n minus 1 plus now third one a n minus 2 f n minus 2. So now we have three coefficients to worry about, and those are for L0, minus 1, minus 2. So as before, the sum of all coefficients should be 1. Now for L equals, for next level, so for L equals to, so now let's, so this is for this guy. So now for the first derivative of f, what we have, this coefficient an again equals to 0, because L equals to, like index in front of it equals to 0, L equal to 0, so we don't consider it. For a n minus 1, we have coefficient, so L equals to minus 1, so it's minus here. And here, this is first derivative, so it's 1/2. And for n minus 2, so we have a n minus 2. So L becomes minus 2, so it's minus 2 equals to that, to 1/2, to this guy. So now next equation, because we have three coefficients, we need three equations. So the next coefficient is going to be for this derivative. So again, in front of an is going to be 0, because L is 0. Now for coefficient a n minus 1, so L is minus 1. L squared, so minus 1 squared becomes just 1 over 2, so it's 1/2. And now L equals to, so it's a n minus 2. So L minus 2 squared, it becomes 4, divided by 2, it becomes plus 2. And equals to this guy, did I do it? Cube, this is 6, yes. Sorry about that. Yeah, it should be 6 here. Fortunately, we didn't use it yet, so we're fine. 1, 6. So if you solve those, I will not do it now in the interest of time. So you get the following coefficients. It's 23, 23 twelfths minus 16 twelfths and 5 twelfths. And this is Adams-Bashforth third order, and of course its truncation error in time is delta t cube. So it's pretty accurate in time, and it has, of course, two computational modes this time, because we have now 3 time levels involved here on the right hand side. Actually, we have, So we have 2 computational modes, and one in physical mode and 2 computational modes, so the total number of modes is 3. But those two computational modes also very effectively, even more effectively than in Adams-Bashforth second order, damped by this scheme. So because it's, remember, this is this scheme is odd order in time, which means that it's actually the truncation error leading term is dissipative. So it's actually dissipative in time, and it's actually it dissipates those computational modes very nicely. So the computational modes for this scheme even lessen the problem than for Adams-Bashforth second order. And this is a nice scheme. So now I maybe spent a few minutes explaining how you actually use it. You use all this f here. It doesn't mean that you actually compute your right hand side 3 times on each time step. well, of course you probably understand that, because you just reuse those previous ones that you already computed. One problem that was here, what to do on a very first time step. On very first time step, when n equal to 1, or n equal to n plus 1 equal to 1, so this one is your initial conditions, that's no problem. But what's about next time step, where you get those n minus 1 and n minus 2? Well, you don't get them from anywhere, you just don't use the scheme for this case. So in that case, on the very first time step, you use earlier scheme. Yes, it's unstable, but it's not gonna produce some terrible thing in one time step. So for the first time step, you use Euler. For the second time step, you use Adams-Bashforth coefficients. For the second order Adams-Bashforth coefficients, and on the time step 3 and further, you just use Adams-Bashforth third order, because now you have all the right-hand sides. So that's not a problem. Okay, so that's a very kind of a scheme, a family, and you can keep going. You can derive easily Adams-Bashforth fourth order and so on. We're not going to do that. But that's basically very nice way to use forward in time scheme and advance, and it's third order accurate in time, even though it's just forward in time. Okay, so another type of scheme is of course implicit, and we already talked about that. It's a simple scheme like this, equal to right hand side of the time step n plus 1. Well, it's first order in time. It's unconditionally stable usually for most operators. F, like advection and diffusion, so it's unconditionally stable, but it's difficult to solve because of its implicit nature. And more popular than this one because it's kind of forward and it's a little bit non-symmetric. So better one is to use is so-called Crank-Nicholson or trapezoidal. I don't know how to read them. Nicholson. Or trapezoidal. Or trapezoidal scheme. It's phi n plus 1 minus phi n divided by delta t equals to average, in this case, n plus 1 plus 1/2 fn. So it's still implicit because you still have n plus 1, but it's still unconditionally stable with most right-hand side operators. So it still preserves, but why bother? Well, first of all, it's delta t second order accurate. And second of all, why people kind of like it, because that's a scheme that allows you to preserve almost exactly the kinetic energy. Because this scheme actually preserves quadratic things too. Well, we're going to talk about that later, but because of this averaging, it actually preserves quadratic quantities. All right. There are many other schemes like that, like Adams Moulton schemes, which is also has this implicit. So when you add some n minus 1 and so on, but it also has this implicit component to it. But they have all the same drawback that as implicit schemes, they're just higher order in time. And but the advantage of them, you can use longer time step because they conditional. They usually I'm not sure that they unconditionally stable anymore. If you keep adding explicit terms, probably it starts dropping. This is probably the last scheme that is still unstable, like an implicit scheme, Crank-Nicholson scheme, still unconditionally unstable. And if you keep adding other terms, stability starts, will be controlled. There will be some stability criterion, but probably not as as strong as mu should be, current number should be smaller than 1, but still there is one. So, but the nice thing, because it's a second order, for example, this one is second order, you can use the longer time step, and of course you can use as long as you want, but the problem is, even though it's stable, if you use very long time step, like in this scheme, but it's only first order accurate, so your solution will be very kind of, smooth solution. It's going to be very large implicit diffusion. So this scheme would be better in this regard, even though your time step is very large, but your solution will be better, approximate actual solution than this scheme. So that's why people use higher order schemes in time for implicit schemes. Okay, so then another type of schemes, completely different. So this one so far it was just approximating right hand side using several time steps. Another class of schemes that people but still use kind of forward in time philosophy is so-called predictor-corrector schemes. So basically, good example of that predictor-corrector schemes is a Matsuno scheme. So basically what it does, first it does some provisional solution, this star, using just Euler scheme. So it's unstable, but that's only one time step you do. So it's not going away too far. So you first do your Euler step, and then you improve it again by running it again. But this time your actual solution minus phi n over delta t. So you still, here you have n, not star. But right hand side is used by using star. Your provisional solution. So this is first step, this is second step. So this is called Matsuno. Matsuno scheme. It's actually been quite popular in early years of general circulation modeling. So several models actually used Matsuno scheme for general circulation model or one of those first climate models. Now it's kind of out of favor, but it's a pretty actually nice and simple scheme. You just use your Euler scheme twice. The disadvantage with previous approach that actually you compute on each time step, you need to compute your right hand side twice. So first you do it for provisional solution and then for predictor state. So this is predictor and this is corrector step. So first you do, but you compute it twice on each time step, and if you have like very long expression for your right hand side, that could be expensive. Unlike Adams-Bashforth scheme, when we compute right hand side, even though we have 3 right hand sides there, for example, for third order Adams-Bashforth scheme, but we compute one of them only. Other 2 we use from previous time steps that we already computed. But here you cannot do that. You need to compute right hand side twice on each time step. So that's drawback. But it's accurate to delta t squared. Oh, actually no, it's still first order accurate. So even though you do this twice, it's still first order accurate. Okay, next, another scheme is a so-called Heun scheme. I don't know how to correctly pronounce it. Or also Runge Kutta, second order. So Runge Kutta is a general kind of family also of schemes, and probably Heun came up with a scheme before Runge Kutta, second order, was kind of generalized, so that's why it's called by his name. So it's another Runge Kutta second order. So it's a Heun scheme, and it's the following that. So you do this predictor step first, similar to Matsuno. So it's similar to Matsuno scheme, or just earlier step. But second step, corrector step, you do the following. Instead of just using this, you may guess it. You just use some average. So, and this is delta t squared accurate. So it's better than the Matsuno scheme, and it actually doesn't introduce any particular more computations, because you still reuse your right hand side here from here, and here you compute a new one. But you still need to compute right hand side twice. But if you do it like averaging like that, you improve accuracy of your scheme relative to Matsuno scheme. Even though the amount of computation is basically the same. And so Runge Kutta is very popular approach actually recently, like WRF model, WRF model, this kind of weather forecasting leading general research kind of model, cloud resolving model in the US and probably in the world too. That model uses so-called also Runge Kutta for time differencing, but I don't know which specific it uses. Probably can specify it, maybe third order, but the most accurate one is the Runge Kutta fourth order scheme, which is okay. I'll write it. Maybe I won't write it, but because you can actually Google it. I don't just want to write it. So fourth order probably is going to be in homework to solve some simple equation. So Runge Kutta involves four. So it's similar to this Runge Kutta second, but here you have predictor and corrector. There you have three predictors and one corrector, or it's basically predictor-corrector, like previous corrector serves as a predictor for next corrector, something like that. And or actually, something. So it's more complicated scheme, but it involves computing right hand side 4 times. So 4 times. So right hand side computed 4 times instead of 1 time in a Adams-Bashforth scheme, and it's a delta t to the 4th power. So it's very accurate in terms of time, but at 4 times. One of the reasons why people use it, especially like WRF, because WRF is a compressible model, and compressible model has sound waves. And remember, in one of the previous lectures, I talked about stability of compressible models, that they actually controlled, restricted not just by the wind velocity or advection velocity, but also mostly by speed of sound. So because WRF is a compressible model, it has very strong restriction on a time step, and Runge Kutta first order allows you to use current number of about 2 and even slightly higher. So instead of 1 for upstream bias, you can actually use current number of 4 or of 2. So twice, your time step can be twice as long, but still, because they're controlled by sound waves, it's still pretty small time step. So, and it's very accurate in time. That's why people. But you need to compute 4 times. That's expensive. Can be very expensive. But people kind of still there are some other nice properties. So people. There is. The choice of numerical scheme is always compromise. Like, you want one thing, advantage in one thing, and then you have some cons, and you have some pros and some cons. So it's always compromise. So some models use some models. Actually, I know, I think 2 or 3 models that I know they use Runge Kutta for time integration of the differential equations. Okay, so I think I stop here. See you next time.